Hello everyone. This week's topic is photosynthesis, climate, and water. We'll be looking at how photosynthesis by plants, especially trees and forests, has a worldwide impact on temperature and water cycling. So let's start off by thinking about carbon. Here's the periodic table of the elements, and here's where you find carbon on it. So carbon is a key element for life. All of our bodies contain a lot of carbon, and trees and other forest plants also contain a great deal of carbon in wood and in leaves, and forests also contain a lot of carbon in their soils. So carbon is a big deal because properties of the carbon atom make it especially good for building life forms. And here in the lower right-hand corner, here's a depiction of the carbon dioxide molecule, which we'll be getting to in a moment. So let's do a quick review of photosynthesis by plants. Here in step number 1, the plant draws up water from the ground through its roots. So most of the time, plants get their water from water that's contained in the soil, and that water moves up the plant against gravity until it gets to a leaf. Meanwhile, at the same time, here in step number 2, the leaves are taking in carbon dioxide from the air. So you have carbon dioxide and water meeting in the leaf, and then here's the sun shining on the leaves and providing energy that's needed to power the photosynthetic process. Once the chemical reactions of photosynthesis are underway, oxygen is given off as a byproduct. That's how oxygen gets into our atmosphere. And then, in addition to producing oxygen, photosynthesis also generates sugars that plants use for food. So here in step 3, the production of sugars. So here's a summary of photosynthesis. What goes in: carbon dioxide, water, and solar energy. What's produced: sugars for the plant's use and oxygen. So how does photosynthesis by an individual tree, for example, participate in a broader carbon cycle that takes in the whole planet? So here you have sunlight shining down on the tree to power photosynthesis. You've got the carbon dioxide gas from the atmosphere going into the tree. What was gaseous carbon dioxide now becomes the carbon that makes up the solid leaves and the solid wood. Eventually, over time, leaves will drop down to the ground. Someday the whole tree will die, and at that point, decay organisms break down the tree, and that carbon becomes organic matter in the soil. Now, at the same time, you've got what's called respiration, which is performed by animals like this little sheep here, also ourselves as people. Note that plants also perform respiration, and so do the decay organisms in the soil. And respiration involves taking in oxygen, which is then used to produce energy, and releasing carbon dioxide. So we as people breathe in oxygen and then breathe out carbon dioxide. So this is a natural way by which carbon from our bodies then goes back up into the atmosphere. Now, down here in the ground, you have what are called fossil fuels. And of course, we hear a lot about fossil fuels these days. So fossil fuels are basically very old plant matter that got buried deep in the soil and compressed. Now, the carbon from the plant tissues is still there. So when we take fossil fuels out of the ground and burn them for energy, we release carbon back into the atmosphere in the form of CO2. So here, for example, auto and factory emissions are taking those fossil fuels out of the ground, bringing the carbon back up, and turning that into CO2 that ends up in the atmosphere. Note that here in the corner, you also see the ocean, and the ocean has very important roles to play in the carbon cycle. There are photosynthetic organisms in the oceans. The oceans absorb quite a lot of our CO2 emissions. And in this class, we'll be talking quite a bit more about oceans and sea level rise as we go on. Okay, so once we get into the burning of fossil fuels, that brings us to the question of climate change. So is climate change happening, and is climate change caused by humans? And I want to start off by saying right away that you don't have to believe in human-caused climate change to do well in my class. Everyone should understand what the theory of human-caused climate change says and be prepared to make your own decision about whether you believe it or not, and then to be able to defend what you believe. Just to put my own cards on the table, I certainly do believe that human-caused climate change is happening. The scientific consensus on it is very strong at this point, and I've seen the evidence for human-caused climate change just building up and building up over my own lifetime. So one of my favorite pieces of proof for human-caused climate change is what's called the hockey stick graph by Michael Mann. And I like the hockey stick graph because it brings together history and science in a form that's kind of memorable, and it's the form that looks kind of like the hockey stick. You have the gradual decrease through here, and then the sudden rise at the end, kind of like the hockey stick gradually goes down and then comes up at the end. So again, here on the bottom axis, you have historical time from the year 1000 through a little bit past the year 2000. And then here on the y-axis, you have temperature. So if we start here, kind of in the European Middle Ages, the general trend is declining temperature, although, it bounces around some. Same thing keeps happening in the Renaissance, the early modern period in European history is what I'm referring to here. And then here in the 19th century, we're getting into the time period of the Industrial Revolution and afterwards. And that's when there are a lot more machines, and the machines are burning fuels like wood and coal that release a lot more CO2 into the air. And as these technologies from the Industrial Revolution become more widely used and spread around the planet, then in the 20th century, we see this really huge and sudden spike in temperatures. So to my mind, the fact that that spike in global temperatures happens, as human beings start to burn a lot more fuels that release CO2 into the atmosphere, is pretty clear evidence that changes that we're seeing in the climate right now do come from human actions and not from other causes. And here's just a sort of dramatic picture that I kind of liked of human emissions into the atmosphere, and someone's gotten that to write CO2 up in the sky. Okay, and we're all seeing these headlines all the time at this point. Here's one from January 2020, about a year ago, saying that Earth had its second warmest year in recorded history in 2019. The 6 warmest years in recorded history have been the past 6, 2014 to 2019. Then data for 2020, which is out now. NASA finds that 2020 is tied for the hottest year on record. If you want to look up that link and read more about what NASA has to say, you can. But we're seeing these records being set all the time at this point. There's not too much question that something unusual is happening. Okay, so how does climate change cause the planet to get hotter? Now, it used to be that people did not say climate change. Instead, they just said global warming. And that's because the increase in temperatures on average worldwide is one of the most obvious effects of climate change. But climate change, as we'll see throughout the semester, has many other impacts as well. For example, sea level rise, increased violence of storms, and that kind of thing. But as far as temperature, what is it that causes climate change to make temperatures rise? So this is what we call the greenhouse effect. Imagine a greenhouse that has glass walls, that has a glass ceiling. Sunlight comes into the greenhouse, it warms up the greenhouse, but the heat stays in the greenhouse and doesn't get back out, and that's why the greenhouse stays warmer than the surrounding temperatures. So here's sunlight shining down onto the Earth. Some of the solar radiation immediately bounces back out to space, and that's not what's heating up the Earth. But you have other sunlight that comes down and gets absorbed by the Earth. and then it gets re-radiated back out as infrared radiation. That's here. And it's as that gets re-radiated back out that it's trapped by what are called the greenhouse gases, which are, in the atmosphere. So carbon dioxide, methane, water vapor, these are some of the most famous greenhouse gases, especially CO2. And a greenhouse gas is a molecule that has special heat trapping qualities. So it traps the heat that's sort of trying to get out from the Earth and ends up re-radiating a significant amount of it back down to the Earth. And the more greenhouse gases that you have in the atmosphere, the warmer that the Earth is going to stay. So I often think of greenhouse gases as being kind of like a blanket. They blanket the outside of the Earth. And if you put a blanket on yourself, the thicker that blanket is, the warmer it's going to keep you. And it's similar with the greenhouse gases. The more of them that they are, the more of them that there are, the thicker of a blanket there is around planet Earth, and that heats up the planet more and more. Okay, so of all of the greenhouse gases, carbon dioxide is considered the biggest culprit, and it's a good idea to keep an eye on the current atmospheric concentration of CO2 and to understand what that number means. So we measure CO2 in parts per million, meaning of a million particles floating around in the atmosphere, about 415 of those are going to be carbon dioxide. So that doesn't sound very much, and as a unit of measurement, parts per million is used for substances that are relatively low concentration in the atmosphere. But CO2 is very powerful when it comes to trapping heat. So even 415 parts per million is enough to warm up the planet quite a bit. And the exact number varies a little bit depending on which source you're looking at and exactly how they do their measurements. But this is approximately where we are right now, and that number is rising pretty continuously. Now, people who are skeptical that rising temperatures are being caused by human activities sometimes like to point out that these high levels of CO2 and higher temperatures actually have happened on the planet before, because there are lots of natural fluctuations of climate on planet Earth. And that is actually the truth. There have been high CO2 levels before, there have been higher temperatures before. However, this was before human beings were on the planet. So we have not experienced these high CO2 levels. We have not experienced these higher temperatures before, and that's really the issue. So here's a quotation that I like at the bottom. The last time CO2 levels were this high was during the Pliocene epoch 5.3 to 2.6 million years ago, when the Earth was several degrees warmer, sea levels were an estimated 50 feet higher than they are today, and forests grew as far north as the Arctic. So in this much earlier time period, forests existed at northern latitudes where we don't find them right now. Sea levels being 50 feet higher is a really big deal. We'll be looking at sea levels throughout this class as we talk about our common reading Rising by Elizabeth Rush, and you'll come to understand that 50 feet more of sea level would really have very dramatic effects on our coastlines and our way of life. Okay, so a few definitions to help you understand readings about carbon cycling and climate change. When we say carbon source, that means something that puts more CO2 into the air, making climate change worse. So if I put gasoline into my car, that's a fossil fuel, and I drive my car powered by gas, my car becomes a carbon source because it's putting CO2 up into the atmosphere. Carbon sink is the opposite of carbon source. A carbon sink is something that takes CO2 out of the atmosphere, thereby slowing climate change. So we've seen that trees, by their nature, hold a lot of carbon in wood, hold a lot of carbon in leaves. Soils where organic matter is contained also hold a lot of carbon. So intact forests can serve as important carbon sinks. Carbon sequestration is similar to the idea of carbon sink. Carbon sequestration is when carbon is stored someplace away from the atmosphere, slowing climate change. So forests can sequester carbon both in plant tissues and in soil. And although we won't be really discussing it in this class, note that many other natural ecosystems, grasslands, peat bogs, plenty of ocean ecosystems also sequester carbon in very important ways. It's not just forests. Okay, so now let's move from carbon to water, water being H2O. So water is another substance which, like carbon, cycles constantly between forest organisms and the atmosphere. So let's go back to photosynthesis, but specifically focusing on the movement of water through a plant. A little tiny illustration here. So water is usually absorbed by the plant's roots from the soil. It then travels upwards into the leaves. And as we saw in the previous slide, oftentimes the water gets used for photosynthesis, going into the photosynthetic process. But there's also quite a lot of water that never gets used in photosynthesis, and that water is lost from the leaf pores through a process called transpiration, also known as evapotranspiration. So leaves have little pores in them called stomates or stomata. And these pores function for two important things. One is that carbon dioxide goes into the leaf through the stomata. The other is that water vapor leaves the leaf through the stomata, exits the leaves through the stomata. So as the water departs from the leaf, it's transformed from liquid water into gas, water vapor. And that transformation requires an input of heat energy to make it happen. And that heat energy comes out of the surrounding air and in the process cools the surrounding air. So evapotranspiration cools the local region that's right around a tree or a plant. So say that it's a really hot day in the summer and you go into a forest or a city park that has a lot of trees and you suddenly feel cooler. Well, that's partly because of the shade of the trees, but it's also because the evapotranspiration of the trees is literally cooling the air. So in that sense, the movement of water through a plant and then out into the atmosphere has a really important effect on temperatures around the plant, and also water cycling across the planet. So here's the title of one of the articles that you'll be reading for this week. And this article has always been a favorite with students in the class. They find it very eye-opening and like a lot of the insights in the article, so I hope that you'll enjoy it too. The article is called Rivers in the Sky: How Deforestation is Affecting Global Water Cycles. And it particularly focuses on the world's large rainforests, like the Amazon, for example, and how the evapotranspiration of trees on a huge scale over the span of an immense rainforest literally affects rainfall, precipitation, and temperatures around the whole planet. So in addition to forests being really important for sequestering carbon, they're also very important for regulating, things like rainfall that agriculture depends on, rainfall that other, plants and animals depend on to stay alive. So I hope that you'll enjoy that article. And then the other thing I've asked you to read is an interview with an expert on the Amazon. And the article is called Will Deforestation and Warming Push the Amazon to a Tipping Point? And this talks more about a big rainforest and, sort of how climate change and other problems are threatening the rainforest, but then in turn, because the rainforest has such an important role for regulating climate around the planet, if the forest itself gets harmed, that causes a whole cascade of other changes. Okay, and at the end of each of my slideshow, I always try to provide links to the illustrations that I've used in the slideshow, and many of these links will also take you to further information on the topics if you're interested in reading a little bit more on your own. Okay, so the next thing to do then is to look at all of the links on As You Learn, some basic review of photosynthesis and carbon cycling, and then these two articles that I've just mentioned. And these will be the basis for both your assignment 2 that's due next Friday, and also for your small group discussions. And you'll get more instructions on those shortly. Okay, so I hope that this was helpful to you, and I'll be back in touch soon.